Good afternoon, ladies and gentlemen. I am Masato Ishikawa from Osaka University, Japan, and I have the honor to introduce today's distinguished plenary lecturer, Professor Laurent Praly, from Paris, France. And thank you very much for attending this parallel session today. And the title of his lecture is on observers, a meeting of many viewpoints and applications. Professor Laurent Praly graduated as an engineer from École Nationale Supérieure du Domaine de Paris, Paris for short, in 1976, and got his PhD in automatic control and mathematics in 1988 from Paris Dauphine University. After working in industry for 3 years, in 1980 he joined the Centre Centre Automatique et Système at Paris again. From 1984 to 1985, he spent a sabbatical year as a visiting assistant professor in the Department of Electrical and Computer Engineering at the University of Illinois Urbana-Champaign. Since 1985, he has continued at the Centre Automatique et Système, where he served as a director for 2 years. He has made several long-term visits to various institutions. His main interest in research is in feedback stabilization of controlled dynamical systems under various aspects, such as linear, nonlinear, dynamic, output, under constraints with parametric or dynamic uncertainties, and disturbance, attenuation, and rejection. On these topics, he has been contributing both on the theoretical aspect with many academic publications and the practical aspect with applications in power systems, mechanical systems, aerodynamic, and space vehicles. So now, please welcome Professor Praly with applause.
Thank you, Professor Ishikawa. So, let's talk a little bit about observers. So when we manipulate data come from the real world, we implement in one way or another what I call an observer. Depending on the field of application, observers take different names: stochastic filters, soft sensors, state reconstructors, data simulation, inverse problems. They are answer to the same problem. Given measurements, which is only partial information, try to estimate internal variable of a dynamical system. In this talk, I briefly go over the general, well-known design rules and give more details on one particular observer, but I shall remain extremely elementary, concentrating only on very basic facts. So there will be 8 parts in this presentation. First, I will see how we can approach the observation problem. Then I will state the observation problem precisely, give some conceptual solution to this problem, deal with observability, then look at what is called the convergence problem, give some necessary conditions to this convergence problem, then with a particular observer with tau possibly non-ejective given h, you will understand later on what this means, and then conclusions. So let's approach the observation problem. The observation problem is to estimate hidden variables, which I will denote Z in this talk, from observed or measured variables denoted Y. The object solving this problem is called, or I call that, as an observer. So measurement makes what is called the a posteriori information, and this a posteriori information increases as data accumulate. So a first sort of an observer structure, an observer is something, an object which takes measurement, which is this a posteriori information, and provide the estimated hidden variable. To illustrate my talk, I will use a simple example, which is how to estimate the length using the pendulum. And this problem was stated and the solution proposed by Galileo Galilei, who wrote in 1638 in his book entitled Dialogues Concerning Two New Sciences. By the way, I recommend reading this book. It is really a fabulous book. I can easily know the length of a string whose upper end is attached, for if I attach to the lower end of this string a rather heavy weight and give it a to and fro motion, and if a friend counts the number of its oscillations while I, during the same time interval, count the number of oscillations of a pendulum which is exactly 1 qubit in length, this is 1 qubit, then knowing the number of oscillations which each pendulum makes in the given time interval, one can determine the string length by taking, and this is a magic name word, the squares of the two numbers of oscillation. I shall divide the larger square by the smaller one, and the length of the long string will be the ratio in qubits. So now in more technical words, the observation problem that Galileo was stating is to estimate a string length from a measurement of the angular position of a pendulum. This looks like very strange. What is the ratio between the relation between the length and an angular position? Well, so definitely we need to know a relation between these two things, between the hidden variable, which is here the string length, and the measured variable, which is the angular position. So my first rule for observer design is that we need a priori information. Up to now I had this a posteriori information, which were the measurement. Now I need a priori information, which is this relation between hidden and measured variables. Usually this relation is not instantaneous, not explicit. It is typically given by a dynamic or sensor models, which are something like the measured variable as a function of time is itself a function of functions which are hidden variables or other, which are also functions of time. So this makes what is called the a priori information. So a more elaborate version of an observer structure is that not only it transforms this a priori information into the estimated hidden variables, but to do so, you need a priori information, which is this dynamic and sensor models. So for Galileo, this relation is simply, as I said, mainly magic name was oscillation number squared. So actually, you can get an estimation of the length just by taking a constant, which turns out to be g over 4 pi squared, then times the oscillation number divided by the observation time squared. So it is sufficient to produce the oscillation number and the observation time from the measured pendulum angle. How you do so? Just look at the cone that the pendulum is describing, divide it into 3 parts, for instance, using the initial angle divided by 2. And then when you are in the middle, the pendulum in the middle part, just do nothing. When it is on the left, namely when the measured angle is more than minus initial angle divided by 2, just set a logical variable pass equal to 0. And when it is on the right, so when the measured angle is larger than this initial angle divided by 2, and if this logical variable was pass was 0, then you set this logical variable pass equal to 1. You increase the oscillation number, and you store the time. So this gives this observer where you have a first block where I have added this dot t equal 1, which is the other pendulum that the friend was counting the number of oscillation that Galileo was mentioning. And then you just have the code of what I presented before. This is just the observer dynamics. And from the information that we have in this observer dynamic, we compute the estimated length is z, the hidden variable, which is just, as I said, the oscillation number divided by the observation times squared and multiplied by a constant. This is the observer output. So this observer is an hybrid dynamical system with continuous variable t, integer variable, oscillation number, and the logical variable pass, and all of that makes a state. And we have also an output function, which is a function of this state. So if I implement this algorithm, I'm showing you here the plots. I guess at the very end you can't read the numbers, but it doesn't matter. What is important is that we have two different curves. So in blue, you have the result I'm getting for an initial angle for the pendulum of 10 degrees, in red, I'm sorry, and in blue, the one for 90 degrees. So as you can see, they differ, but it's the same pendulum. So there is a problem, and the problem is that Galileo's relation is only an approximation for small energy. If you want to be correct, you need to invoke the Jacobi elliptic functions, and I will come back on that at the end. So another way to have a relation is to use Lagrange principle, which tells you that you have conservation of energy. In this case, the mechanical energy is just the length divided by 2 times omega squared plus g times 1 minus cosine theta, and this is a constant. G here is the local gravity acceleration, theta is the angular position, and omega is the angular velocity. So if we know theta and omega as function of time, then we are left with just trying to identify two constant numbers, E and L, and this can be done simply by solving a mean square problem over a window t minus cap t to t of this quadratic criterion. Well, the function theta as a function of time is the a posteriori information. This is given by the measurement. So then we are left with producing the derivative of this theta dot, which is omega the angular velocity, from the measurement. But theta dot is a mathematical concept which involves a limit process. So since only standard numbers can be used, we are led to use an approximation. So I'm using here, for the illustration, the simplest one, which is finite difference. So an estimate of the angular velocity omega will be omega hat, which is just the standard finite difference, theta times s minus theta times s minus h divided by h. H will be the time step. So I'm getting, this leads me to this observer, very simple one. I have omega hat, which is just, as I said, an approximation by a finite difference of the velocity angle, and then you just solve the least square problem, which gives you this L hat. This observer has two parameters, t and h, and it definitely has the structure I was saying, so it is processing a y and providing this L hat, and in this formula is hidden this a priori information, which is just the fact that this mechanical energy is a constant. If I implement that, I'm getting still with, in red, what I get for the initial angle of 10 degrees, and in blue, what I get for the initial angle of 90 degrees. Now the mean value is about the same. So I don't have the same problem as what I had with Galileo's model. But as you can see, it is highly oscillatory, whereas the length is constant. So there is a problem. What is this problem? The angle measurement is actually made with a disk divided into n sectors. So the measurement, y, is the closest integer value of the ratio n over 2 times theta over 2 pi times 2 pi over n. That is, it is the true angle, theta plus q, where q is a quantization error. And this quantization error is in an interval, minus pi over n plus pi over n. The consequence of this error is that the angular velocity estimation has also an error, and it can be upper bounded, as you can see here, with this time step, which is one parameter of my observer, appearing both in the numerator and denominator. So there exists an optimal time step, h opt, and clearly it is decreasing with respect to solution energy, which is hidden behind the sign of theta, but it is increasing with respect to the uncertainty n. So to tune the observer, I need not only to have this relation, but I need to know n, which models the uncertainty. So just to make the things a little bit clearer, in my simulation n is 512, which is 0.7 degrees, and the sampling period t samp is for all the simulation, this h opt. So my second rule for observer design is that in the a priori information, I need also a model of the uncertainty. Another consequence of this interval is that what we can say about the true angle is that it is in the interval y minus pi over n, y plus pi over n, y being the measured angle. So the input we should use for the observer is not a single value y, but it should be the whole point, the whole interval. This leads to an interval for the estimated length. So if I play that, and sampling this interval with the Monte Carlo method, I get for this, using this finite difference algorithm, that the true length should be between the points given by these two curves. It's not a single value, it's just a segment. So rule 3 for observer design. Due to uncertainties, the output of an observer cannot be a point, but only a confidence set or a probability measure or something of this kind, depending on the way you do your model of uncertainties. So now I'm ready to state properly the observation problem. In the observation problem, I need this a priori information, which are mainly models. Here they are written in discrete time, but that could be continuous time, a hybrid system, whatever. So it is made of a first equation, which is xk plus 1 is equal to f of xk and uk. So x appears as a state. And then similarly, you have that yk, the measurement, is function of xk and vk, and the hidden variable, function of xk and wk. Here, u, v, and w are exogenous inputs that you may know or may not know, but you know what is or what is in blue, so you know that the set a priori, you are given this information, so x is in capital xk, y in capital yk, and etc. So what your a priori information is the data of the function f, h, and g, and of the set x to w, or of the probability measure of this set. Then the a posteriori information is that all the measurement you have collected during a time interval, so at time k, you have everything, all this yj with j between k minus cap k to k. Then the observation problem is to give a confidence set or a probability measure for the hidden variable zk. So a correct version of an observer structure is, as we saw, we have this, the observer is working on this measurement, this a posteriori information to provide the estimated hidden variables using a priori information, but a priori information is a dynamic of sensor model plus model of certainty and plus all the a priori you can get. And the answer is not a point, it's a set or probability measure, or it should be. So going back to my length estimation problem, using Newton's law, the a priori information for the length estimation problem can be written on all what is on this line. So the length is constant, L dot is 0. Theta dot is the speed, it is omega. Omega dot is minus g over L sine theta. This is Newton's law. And then we have the measurement due to the quantization. So we know that theta is in this interval, 1 minus pi over n, pi plus pi over n. And we know also that L is strictly positive. So in this a priori information, there is two constants, G and N. G qualifies the model, the dynamic, whereas N quantifies the uncertainty. So we do have the structure I was mentioning in this case. Let's look at some conceptual solutions to this problem. At time k, so the first one will be the set valued estimators. At time k, the hidden variable is in a set zk, which you can compute by the following recursive algorithm, where xk contains the true state, x hat k, contains the true state xk. So as initialization, you cannot do better than your a priori information. So x hat 0 is just x0. But then assume that you have x hat at times k minus 1. Then you can predict what it will be at time k, just using the flow, which is given by the function f, and knowing that the exogenous input uk minus 1 in this capital UK minus 1. So you get a set, which is your predicted set from the information you have up to time k minus 1. But then there is a measurement. The measurement is the fact that yk has to be equal to h of xk and vk. So you can throw away some points of this hat k given k minus 1, all those which are not consistent with the measurement. This is what is written in this line restriction. It's mainly intersection, so you just throw away some points. And then knowing x hat k, you can propose what an estimation for the hidden variable, which is mainly just using the function gk, knowing that the corresponding exogenous variable wk is in this capital WK, and also that this that this hidden variable has to be in the set zk. So all what is in blue is given by the a priori information. I said conceptual. Why? Because can you implement this algorithm in practice? Then you need set approximation. So there are a lot available in the literature: ellipsoid, hypercubes, polyhedron, sampling, many. If I implement this algorithm, in my case, here is what I get, and I'm, in this case, guaranteed to have the true length between these two curves. It's just an implementation of the set value estimator approach. The second conceptual solution is a conditional probability valued estimator. In this case, instead of working with sets, you work with probability of sets. So the a priori information is that the initial condition, x0, uk, vk, and wk, are independent random variables with known probability densities. And you know also, so here what you have on your left is the standard functional description, whereas in the middle you have the equivalent probabilistic description. So for instance, the fact that you know that the initial condition is x0 is equal to chi0 becomes the fact that the probability of x0 being equal to chi0. Similarly, the fact that xk plus 1 is equal to fk of xk and uk is the fact that the probability of xk plus 1 being equal to chi k plus 1, provided that xk is equal to xk and this being at time k, and etc. for all the other things. To simplify and make some analogy with the set approach, I'm writing in blue this a priori information. So all these things are now a conditional probability, but they really look like sets. In this context, the a posteriori information is just a collection of the measurement. So you know at time k that yk was measured, the measured value was psi k, at time k minus 1 the measured value was psi k minus 1 up to y1 being equal to psi 1. And to shorten the notation, I note all this as script yk being equal to a vector psi k, which is just concatenation of all the psi I've seen up to now. So the observation problem in this case is to compute at each time k the conditional probability, namely the fact that the hidden variable zk has value zeta k, knowing a priori and a posteriori information, in particular knowing that script yk is equal to psi k. And I will denote again, with analogy with the set approach, z hat k of zeta k and psi k, this conditional probability. Well, again, you can write down a conceptual algorithm for this conditional probability. It is written here. It's a recursive algorithm where x hat k of chi k and psi k is a conditional probability that x k is equal to chi k, knowing that script yk is equal to psi k. So as initialization, this conditional probability is just the a priori probability. Then assume that you have this conditional probability of xk minus 1, x hat k minus 1. Then again, to predict what it will be at time k, you just use the flow. In this case, it is just given by the Chapman-Kolmogorov equation, which is mainly how you relate joint probability and marginal probability. But then at time k, you have the measurement. So again, you have to make sure that your prediction is consistent with your measurement. How you do that? This is done simply from a technical point of view by bias rules. But what is important is that you see that this blue yk is multiplying x hat of k times given k minus 1. So remember, this is probability. So you just put weights mainly on what your prediction was, given your information. And then from the information x hat k, you can predict, you can give an estimation of the conditional probability hat k we were looking for, again using Chapman-Kolmogorov equation. So it turns out that if all the probability distributions are Gaussian, this is nothing but the Kalman filter. But in the general case, how to implement this algorithm in practice? Again, approximation. So there are approximate nonlinear filters. There are plenty again of them. Extended Kalman filter, incentive Kalman filter, approximative grid-based method, sequential Monte Carlo method, also named particle filters, and many others. These two conceptual solutions I mentioned, this set-valued approach and this conditional probability approach, give a confidence set or a probability measure for the hidden variable. But I may be interested in a single value. How to get this single value? Well, this is rule 4. To get a single value for the hidden variable from the confidence set or the probability measure, you need to know what it is used for. Usually we take a least square whatever, but why least square? What is the motivation for it? Is there any practical interest? So this leads also to the optimization-based estimator. In this case, we quantify what the hidden variable is used for in a cost, acknowledging the fact that the equations of the a priori information cannot be satisfied exactly. For instance, at time k, a single valued estimate z hat k of the hidden variable zk is given by the following algorithm. So at each time k, you solve the minimization problem, which is a cost jk, functions of the exogenous variable u, v, and w on a window k minus cap k to k. And this minimization is done with respect to variable sigma, which is in a set, which has to be in a set capital sigma. This variable sigma is made of the system state chi and hidden variable zeta, again on a window. And capital sigma introduces the a priori information. So on the first line, you recognize the dynamic of the system with this f, and knowing also that x is in capital X and u is in capital U. The second equation is the equation for the hidden variable with this function g and this set capital Z and W and capital W. And the third equation is the measurement. So we have now a constraint that h of the state and this exogenous variable v, which has to be in capital V, has to be equal to 1. When you have solved this minimization problem, then you select z hat k as a component of theta k of sigma in the set of minimizer of jk. Again, how to implement this algorithm in practice? Again, this weird approximation. For the length estimation problem, this optimization approach leads to what is here. So first, I'm writing a discrete time model for it, and for that, I'm just using a small angle approximation, so saying that sine theta is equal to theta, and the notation is that rho is square root of g over L, c is cosine of rho times t sampling, and s is just the sine of rho times t sampling. Then the a priori information in this case, in discrete time, that theta k plus 1 is c theta k plus 1 over rho s omega k. Omega k plus 1 is minus rho s theta k plus c omega k. This is the system dynamics. And then we still have the same a posteriori information that the true angle is in interval yk minus pi over n, yk plus pi over n, yk being the measured angle, and you have still this effect of quantization. Then from this a priori information, we try to get the estimated length by, as the most consistent in a least square sense with the a posteriori and a priori information. That is, we look for this rho bar where rho is including the L, which minimizes its cost. And as you can see, its cost is made of 3 lines. The first line is just penalizing the fact that theta is not in the interval. The second line is just penalizing the fact that the first equality of the system dynamics is not satisfied, and the third one is just the same for the second equation of the system dynamics. If you implement that and simulate it, here is what you get. But still we have a problem because we were supposed to get a constant value, but we still don't have this constant value. Up to now, I've not mentioned the word observability, and people who know a little bit about observer, they know that this has to come to show up. So let's start with some remarks. Without any assumption like observability on the models, the set-valued estimator and the conditional probability value estimator in particular are providing the best possible answer to the observation problem given the a priori and the a posteriori information. But this answer is useful only when the a posteriori information is enriching the a priori one. I mean by that when the a posteriori information allows us to make a better distinction among the hidden variable compatible with the a priori information. Without this information enrichment, we may fear a too strong sensitivity in errors in the a priori information. For instance, if I apply this optimization approach I just showed for using 3 different angles, initial angles for the pendulum, 10 degrees is in red, 5 degrees in black, and 1 degree is in blue. Notice that going from 10 to 5 and then to 1, you reduce the solution energy. And as we see is that as we reduce the solution energy, so when you go from red to black and then to blue, you increase these oscillations. So as we see, as the solution energy decreases, the estimation quality deteriorates. As we'll see extremely quickly later on, it turns out that when the solution energy decreases, it turns out this is related to the fact that the a posteriori information gets worse. So to enter in observability, I will be slightly more specific, or I should say even strongly specific. I look at the system as a continuous time one, and the dynamic is made by x dot equal f of x. The measurement is y is equal to h of x, and I denote capital X of x and t, the solutions, and I denote sigma minus x, sigma plus of x, the maximal time interval of existence of this solution. If the system is time varying, which would be the case if there is some known exogenous inputs, then I just add the time. So x dot equal f x and t, y is equal to h of x and t, but you can go back to the top equations just by replacing x by xe, which is made of x and t, and then xe dot will be f of x and t and 1, which I will call fe of xe, and the same thing for h. But then, in this case, if I go like this, everything will depend on the particular time function I'm considering. Okay, the notion of observability is differential observability without a k. I'm saying that a system satisfies the differential observability property without a k if the function which to x, the state of the system, associate this capital Hk of x is injective. What is this Hk of x? It has k minus 1 block of components. The first block is h of x. This is the measurement. The second one is a derivative of the measurement along the solution of the system, which is obtained by taking the Lie derivative LFH, where this Lie derivative is written at the bottom. Then the third component is a second derivative, which is LF of LFH, which I denote LF square of h, and you have this iterative procedure up to taking k minus 1 derivative. The interest of this differential observability with order k is that if you have this property, then for all capital T strictly positive, the mapping which associates the initial condition of the solution to the whole path, the whole path of the measurement, so h of capital X of x and t with t in the interval 0, capital T, or sigma plus if the solution escaped before, this mapping is injective. It means that as soon as you know this trajectory, this h of capital X of x and t, then you know x. So if there is no uncertainty, the a posteriori information allows us to isolate instantaneously a single hidden variable. And of course, this is the best for information enrichment. So if we go to the pendulum and we compute H4, and I denote Y1 to Y4, the 4 components of H4. Then the first component is the measured angle theta. Second component is the derivative, angular velocity omega. The third component is the derivative of omega, Newton's law, minus g over L sine theta. And the third and the fourth one is just the derivative of this sine theta, so minus g over L omega cosine theta. It turns out that you can recover L theta and omega by the expression which is written here, which are just analytic functions of y1, y2, y3, and y4, except when y3 squared plus y4 squared is equal to 0. But if you compute y3 squared plus y4 squared r, you get this g over L sine theta squared plus omega squared plus cosine theta squared, and this is 0 if and only if the state energy is 0. So from this we conclude that H4 is left invertible when the state energy is non-zero, which is equivalent to say that H4 is injective when the state energy is not zero. And so we have established that the pendulum satisfies this differential observability property with order 4, except for states with zero energy. And remember that the state space of the system is 3. It's only L, theta, and omega. So we have already seen that there is something which is bad when the energy level is small. Remember, we have this very bad behavior, more and more oscillating for the answer of the optimization approach. So I'm interested in this differential observability property because when there is no quantization error for the pendulum, then the set value estimate, the conditional probability valued estimate, and also the optimization-based estimate converge. And as you can see here with the set value approach in red and the optimization approach in black. Okay, so let us move now to the convergence problem. Why do we have a convergence problem with observers? So let's go back to these conceptual observers I was mentioning. These conceptual observers are, again, still taking this measurement, transforming them into the z hat of t. How do they typically work? They transform this time information, which is y as a function of time, the measurement as a function of time, into state in quotes, which I denote as sigma. So this looks like data compression, and I will not go further than this. Then from this sigma, we compute the z hat of t. So we have seen that this state in quote is a set in the set approach. This is what is x hat of t. It's a conditional probability in the stochastic approach. It can be the gradient of the cost in the optimization approach. And it can be the collection of the measurement and its derivative when you use differential observability. In this case, z hat of t, the hidden variable, is also a set in the set approach, a conditional probability in the stochastic approach, and single points both in the optimization approach and using differential observability. But because of approximation, in computing the sets, or in computing the conditional probabilities, or in the optimization, or in measurement derivatives, or simply in computing the observer output, a real observer is only an approximation of the conceptual observer. So a better representation of observer is something like this, where I've simplified a lot they looks like a finite dimensional dynamical system, but it could be much more complicated than that. So an observer will have something, what I mean by the first equation, psi dot is equal to phi of t, psi, and y, is that there exists a dynamic with some state. The state here is written like psi, and the dynamic is represented by a function phi, but it could be something more involved. Remember that we saw this hybrid observer coming from Galileo's relation. And then from this state, in quotes, we get this z hat, via an output function which I will denote tau. So for me, an observer will have a dynamic phi and an output characterized by tau. And so the output is the z hat of t, but remember, it can be a set or a conditional probability or just a single point. So the observer convergence problem is, at least when there is no uncertainty, do we have that this output, z hat of t, converges to a single point, z of t, which is the hidden variable for the particular solution we have, which is capital X of x and t, if the solution exists on 0 plus infinity, or within the domain of existence of the solution, which would be 0 sigma plus if the solution is k infinite time. So let us look now at necessary conditions for convergence. I will be even more specific to do that. I consider that I'm given distances dx for on the state space of the system, dx on the state space of the observer state, which is Rm is here, so an Euclidean space. Then the system is defined by my two functions f and h. Dynamics is x dot equal f of h, x. The measurement is y is equal to h of x, and the hidden variable is simply the state to make the thing simpler. And I'm assuming that O evolves in an open set O of Rn, whereas we may have P measurement Y in our Rp. Note that there is no uncertainty here, so we have a perfect model. Let the observer be defined by two functions, as I said before, this function phi and tau, so in a similar way as for the system, with psi in an open set omega. And the output of this observer is x hat, so the estimation of the hidden variable, which is the system state in this simplified case. The assumption I'm making now are there will be two assumptions. First one is reg for regularity, is mainly that the functions f, h, phi, and tau are local ellipses. And moreover, I'm assuming that all the solutions of system and observer with values in O cross omega can be right maximally defined on 0 plus infinity. Second assumption conf for convergence. Remember, I'm trying to look at necessary convergence for convergence, so that will be one assumption. Then we have convergence. So I'm assuming that the zero error set, which I denote script E, which is the pair of system state x, observer state psi, which are in O cross omega, such that x is equal to x hat. X hat is, remember, is tau of psi and h of x. I'm assuming this set is asymptotically stable with domain of attraction containing O cross omega. So we have the following proposition. So in the context I defined, and under these two assumptions, reg and conf, we have that there exists a subset O0 of O and a set-valued map which to x associate the set tau star of x, subset of omega, such that this zero-error set can also be written as a set of pairs x chi in O0 cross omega, such that chi is in tau star of x. This is mainly saying that the observer output function tau has to be surjective, but in a strange way. It has to be surjective, but you have this extra information that you know h of x. Second, this set O0 and script E are forward invariant. Second property to convergence is that we can describe the asymptotic stability of the script E of this zero error set by a Lyapunov function. Namely, there exists a C-infinity function V defined on 0 cross omega with values in R plus, and two class K-infinity function underline alpha and overline alpha, and a continuous function omega bar, such that the derivative of V along the solutions of system and observer coupled, so namely the Lie derivative along f and phi of V, is more or equal to minus V. And also this function V is switched between alpha underline and alpha overline of the distance between x and x hat, so which I write as d sub x of x and x hat again is this tau of psi and h of x. But in the upper bound, you can allow the distance to be multiplied by this omega bar of x and psi. So again, this is a necessary condition. If you have convergence on observer, you do have existence of such a Lyapunov function. But this Lyapunov function is in general function of the two variables x and psi, so the state of the system and state of the observer, and for sure not only a function of x minus x hat, that is of x minus tau of psi and h of x. Let's see what happens if we restrict this argument to be x minus x hat. So under assumption reg, if there exists a C1 Lyapunov function, V, which is positive definite, so namely V of x minus x hat, so V of x minus tau of c and h of x is positive. And again, the Lie derivative of V along the solution system and observer solution, so L along f and phi of V evaluated at x minus x hat, which is this tau of c and h of x, is strictly negative when x is not equal to x hat, then necessarily the function which associates to X the pair f of x, h of x has to be injective. So the important point here is that I was restricting V to be x depending only on x minus x hat. And notice that this is a coordinate-dependent condition. So let's see what this gives for the length estimation. For the length estimation, the state of the system is L, theta, and omega. The pair f of x, h of x is f of x is just the speed of the state. So L dot is 0, theta dot is omega. Omega dot is minus g over L sine theta. And then you have the measurement theta. Well, this mapping is not injective on the set of strictly positive energy states. Look at what happens when sine theta equals 0, L disappears. And of course, the pendulum goes, on each period, it goes through this theta equals 0. Conclusion, there is no observer for which asymptotic stability of the zero-error set, script E, can be established with a strictly Lyapunov function depending only on L minus L hat, theta minus theta hat, omega minus omega hat. Another necessary condition for convergence is that under assumption reg and conv, if the observer output function tau is injective given H. So you have already surjective given H, now it is injective given H. So the way to define that is that if there exists a class K infinity function alpha tau such that the distance dxc between xa and xb is more or equal to this alpha tau of dx of xa and call it xb. xb is the output of the observer when the state of the observer is psi b and the measurement sent to the observer is h of xa. And the relation between xa and xa is that xa belongs to tau star of xa that we saw before. Then in this case, tau star is single valued, and there exists a function L such that the dynamic of the observer function phi can be decomposed as a sum written here. So phi is the Lie derivative of tau star along f evaluated at x hat, which is tau of psi and y, plus this term L of psi and y, where this term is 0 when h is equal to h of tau of psi and y. In other words, the observer dynamic is a copy of the image by tau star of the system dynamic plus a correction term which is 0 when actual measurement is equal to estimated measurement. Hence, in some coordinates, the decomposition, which we see very often on observers, that is, the observer dynamic is a copy of the system dynamic plus a correction term, is necessary when the observer output function tau is a bijection given h. So that is when there exists a function tau star such that you have surjectivity, which is the fact that you can reconstruct x from tau star of x knowing h of x. And injectivity is the same thing. You can reconstruct xi using tau star and when y is equal to h of tau xi and y. So my fifth rule for observer design is that for an observer to have the convergence property with an output function tau, which is a bijection given h, the dynamic of its state psi must be a copy of, well, in some coordinates, a copy of the system dynamics plus a correction term which is 0 when y is equal to h of tau of psi and y, that is when actual measurement is equal to estimated measurement. But the important point is that there is no such rule if the output function tau is not injective given h of x. So let us look at what this means that an observer with tau possibly non-injective given h. The most frequently encountered observers have an output function tau which is a bijection given h. But we know at least two families of observers with tau possibly non-injective, given h. This is the high-gain observer with immersion and the nonlinear Leuenberger observer. Since this nonlinear Leuenberger observer is less known, I will focus my attention on it now. The result we have is that if you assume the set O where x is leading is forward and backward invariant, and we have an integer m, a U-bit matrix A with complex coefficients, identified m cross m, and two continuous functions, tau star and b, and finally a class K infinity function rho, such that tau star admits a Lie derivative along f, so LF tau star exists, and solve what I call here PDE, so LF tau star of x is equal to A tau star of x plus B of h of x. And second, you have this inequality that the distance between x1 and x2 is more equal to this function rho evaluated at the distance dc between tau star of x1 and tau star of x2. So this is mainly saying that tau star not only solves PDE but is also uniformly injective. Then in this case, there exists a continuous function tau such that the observer written here, where the dynamic function phi is simply xi plus dy, and the output is given by this function tau, so x hat is tau of xi. This solves the observer convergence problem. This is a nonlinear Leuenberger observer. Its tunable parameters are the integer m, which is the dimension of the set xi, the matrix A, and the function b. Two comments. The first comment is that the observer output function tau is in general not a bijection given h. The consequence is that the observer dynamic function phi is not a copy of the image by tau star of this system dynamics pressure correction term, which is 0 when actual measurement is equal to estimated measurement. But we are seeing that to have this result, we need this tau star solution of PDE, and which is also uniformly injective. So what about existence of a solution to this PDE? Where we have that for each U-bit complex matrix A in MM, we can find a C1 injective function B such that there exists a continuous function tau star solution of PDE. So the fact that we have a solution to this PDE is more or less trivial. The fact that we know we have explicit expression in another things, but theoretically, existence of solution is not really a problem. For the length estimation problem, here is what it gives. Let lambda I be complex numbers with negative real part. The nonlinear Leuenberger observer dynamics are simply xi dot. Xi I dot is equal to lambda I xi I minus sine theta, where there is I is between 1 and m. This is simply picking the A matrix as a diagonal matrix, lambda 1 to lambda m, and the vector B, and B as a vector, lambda 1 to lambda m, multiplied by sine theta. The corresponding PDE with tau I star being the unknown is simply d tau I star d theta times theta dot, which is omega, plus d tau I star d omega times omega dot, which is minus g of L sine theta, plus d tau I dt if I allow tau I star to be t dependent. This has to be equal to lambda of tau I star minus sine theta. There exists a solution in the form, very simple form, which is CIL function of time times g over L, L being my unknown, plus Ci omega of t times omega, which is also not measured, plus sine theta. And the CIL and Ci omega are given by the ordinary differential equation written here. So CIL dot is lambda I CIL plus Ci omega sine theta, and Ci omega dot is lambda I Ci omega minus cosine theta. So not only we need a solution to this PDE, but this solution has to be uniformly injective. So assume the system satisfies, and we are back with this notion of differential observability property. So assume the system satisfies the differential observability property with some order on the set O. Then if we select M equals to n plus 1, there exists a positive real number mu and a subset S of Cm with 0 Lebesgue measure, such that with A made of the diagonal of the lambda 1 to lambda m, and the lambda I are arbitrary complex number in Cm, but not in S, which, remember, this S has 0 Lebesgue measure, and with real parts strictly smaller than mu, then tau star, we can find tau star solution of PDE and also injective. And it turns out that on compact set, continuity plus injectivity implies uniform injectivity. So mainly, as soon as we have differential observability property on some order, at least on compact set, we can write this nonlinear Leuenberger observer. For the length estimation problem, remember these two ODs I was giving to define the CIL and CI omega. They are written here on the top. Then you make a matrix with two columns. On each row you have C1L and C1 omega, and then C2L, C2 omega, up to CML and CM omega. And then in this case, tau star is simply this matrix multiplied by the vector G of L omega plus a column vector of 1 times theta. And it can be shown that it is sufficient to pick m equal 3, where complex number counts for 2, eigenvalue lambda I to obtain the matrix M3 with rank 2. At least for solution with small but non-zero energy. Actually, for m equal 3, given theta and t, the function which associate to omega and L, the tau star of omega L and T, is injective on the set where L is strictly positive and the state has a strictly positive energy. So at the end, the nonlinear Leuenberger observer for this system is that we have 3 times what is written here, so I is between 1, 2, and 3. So psi I is, as we saw before, lambda I psi I minus sin theta. CIL dot is lambda I CIL plus CI omega sin theta, and CI omega dot is lambda I CI omega minus cosine theta. With the CIL and CI omega, you make this matrix M3. You take the pseudo-inverse of M3, you know it is rank 2, so you see it in the denominator, and you use psi to get also in the denominator to get this L hat. And here is what it gives. Again, I'm showing not a single point, but a confidence interval. So the estimated length should be between the two curves. And again, how do I get that? It's because I know that the measurement is in an interval, and I'm using Monte Carlo method to know, trying to know what the confidence is. Some extra comments on this nonlinear Leuenberger observer. We have an approximation, so when you cannot solve the PDE, either you go with discrete or you go with analytic approximation. And in particular, there is a relation between high-gain observer because they can be seen as an approximation of Leuenberger observers. But we have no theory available yet on how to select the tunable parameters M, A, and B. In particular, I started my talk with giving 5 rules. So rule 1 was, and we will see them later on, rule 1 was use a model of the system. This is indeed done in this nonlinear Leuenberger observer. But rule 2, 3, and 4 was dealing with uncertainty. And I don't know. I don't know how to deal with uncertainty with this Leuenberger observer for the time being. So we are now getting to conclusions. The observation problem is to estimate a hidden variable from a measured variable. And I call observer the solution to this problem. To design this observer, there are at least 5 rules. Rule 1, we need a priori information as a relation between hidden and measured variables. Rule 2, in the a priori information, we need also a model of the uncertainties. Rule 3, due to uncertainties, the output of an observer cannot be a point, but only a confidence set or probability measure of something of this kind, depending on how you do your model, your uncertainty model. Rule 4, to get a single value for the hidden variable from the confidence set or the probability measure, you need to know what it is used for. Rule 5, for an observer to have the convergence property with an output function which is a bijection given the measurement, its state dynamic must be a copy of the system dynamic plus a correction term, which is 0 when actual measurement is equal to estimated measurement. But there is no such rule if the observer output function is not injective given the measurement. Observers whose output function is not injective given the measurement do exist. High-gain observers with emission or nonlinear Leuenberger observer. What they exploit actually is dynamic extension. The domain of application is much broader than the one which imposed this output function to be bijection, which are much more typical and standard. For the future, Well, it's clear that with progress in both theory and technology, the conceptual approaches will be less and less conceptual and more practical. So set-valued estimators, conditional probability valued estimators, and optimization-based estimators will become very efficient tools. And they can be used already for a slow dynamic system or with reduced number of states. But other techniques will remain appropriate. It turns out that by combining Galileo's idea with Jacobi elliptic function, we get a robust, I've not said robust, but I not mentioned this word up to now, but let me add it here without any being very specific. And more importantly, a very fast algorithm which gives this. So we have corrected, again, in red, you have the 10-degree initial angle, in blue, the 90-degree. So now you see that they are the same because we have corrected the Galileo relation using Jacobi elliptic functions. And as you see, also the confidence interval is getting very small. I have to apologize. I have not given a single reference in this talk. And this is a choice I had to make in view of the too many contributors I would have had to name. And there are plenty in this room now that I can see. If you want more information about this, please contact me. And finally, I would like to thank very much Professor Alberto Isidori, who is the president of Ifac, Professor Sergio Bitanti, chair of the International Program Committee, Professor Eduardo Mosca, chair of the National Organizing Committee, for their extremely honorific invitation in giving this panel plenary lecture. I thank also very much all the colleagues I have been working with, in particular on this observer topic, and from whom I learned so much. Vincent Andrieux, Murat Archak, Alessandro Astolfi, Georges Bastin, Alberto Isidori, Jean-Luc Lamblard, Jean Levin, Lorenzo Marconi, Romeo Ortega, Ricardo Sanfelice, Jungbo Shim, Andrew Till, and many others. Finally, I thank my institution, MIN Paris and my research center, Centre Automatique et Système, for giving me the opportunity and the appropriate environment to do my work. And finally, I thank each of you for your attention. Thank you very much.
Thank you very much, Professor Praly, for giving us a very stimulating and sophisticated talk on observers with 5 very important rules. And as I was requested by the organizing committee, we do not accept questions here from the audience. So let me just mention that Professor Praly is happy to receive a question from you, and he will be staying here until the end of Congress. So let me close this plenary lecture by thanking again to Professor Praly with big applause.